use the SSID pipette. You fetch pipette. Yes, yeah. But it asks for. Let me show you.
Okay, so welcome to the first periodization in keynote. The first speaker of the session is Martin Spinrath, and he is now an assistant professor in National Taiwan University. We'll be talking about detection of cosmic neutrino background. Let's welcome him.
Yeah, thank you everybody. I already apologize because I have to rush. This is usually a 1 hour talk and I have 50 minutes. So I will speed up a bit, yeah? Bad manners, but I will still do anyway. This is based on a paper with Ulrich Domke, and the paper work in progress with Lorenzo Tredi and Josef Zweta. It's in fashion now. They are also kind of on the job market, but they're looking more like for faculty jobs. So anyway. And I will also tell my proposal and some theory paper about it, yeah? This is very important. This is kind of my talk, introduction. These are 3 ways how to do this. I will go to them step by step. Then we'll some questions to do. Let's start with introduction. The cosmic neutrino background. I'm not sure if you're familiar with this one because nobody saw it so far, so we don't talk about it so much. Cosmic neutrino background is the same principle as the microwave background. In the early universe, it's very hot and dense, it cooled down, and then it's not just decoupled, and they should still be around today, unless they decay or something happens. Yeah? But it's a rock-solid prediction of the cosmological standard model together with standard model of particle physics. So we really believe it should be there. But nobody saw it so far. Yeah? And why did nobody see it? I mean, this is all numbers which we would like to test. Yeah? This is your prediction. This has to be verified in experiment. The problem with this, guys, is if all these predictions are correct, we expect a cross-section of the CME neutrinos with neutrons of 10 to minus 27 picobarn. And this is a problem, yeah? Because they see nowadays there's more or less picobarn cross-sections, and this is of course much smaller than picobarn. The good thing about neutrinos is they have huge flux. Yeah? They're basically the highest neutrino flux on Earth is coming from them. Yeah? What are you doing? Thank you. Anyway, this is a large neutrino flux, and you might hope this large neutrino flux can compensate for a small cross-section, but you will see that this is not quite the case. Yeah? This is, I guess you've seen all this picture. This is a Planck picture from the CMV, so you don't get confused. This is not neutrinos. This is more or less the oldest picture of the universe which we have so far. And what I would like to see is this picture in neutrino light. This is based on simulations. We don't know how it looks, so this is just simulations. But this would be a potential outcome of doing the same experiment but for neutrinos. Yeah? And you see it depends on the mass scale. This is for very light neutrinos and for very heavy neutrinos. All the small scale structures are washed out by gravity. Yeah? This is dark matter. We believe it exists. Let's move on. Resonant absorption. I should say, this is also cosmic relic. It's the same story. You will see why I talk about this. Yeah? The first thing I want to discuss is resonant absorption. The idea is very similar to the GCK cutoff. These neutrinos, they are floating all over the space. So you take some high energy neutrino source from black holes, blazars, AGN, I don't know, you name whatever you want. And then this high energy neutrinos will do some resonance scattering with cosmic neutrino background, and you should produce a Z. And because there's a resonance, that means in the spectrum of this high energy neutrinos, you should see a dip, yeah? Because at this energy scale they get absorbed, and then afterwards they can again more or less stream freely. Yeah? So you would expect a dip in the energy spectrum for neutrinos roughly at the order of 10 to 11 GeV, which is very far away from what we see nowadays with the ice cube. Yeah? So there's still a huge gap to fill to see this dip. Yeah? People also try to look for the Z burst, but this kind of they don't do so much anymore, and as far as I know, nobody saw that. Yeah? So let's move on with mechanical forces. This is the paper I was Valerie last year. So the idea is very simple. Yeah? Neutrinos are everywhere, and neutrinos interact with matter. This is good because we know they interact with matter. That means if I take any ordinary material and move it to the neutrino bars, you should feel a tiny recoil force from the neutrinos, yeah? Because neutrinos will push against the material, yeah? Just from the relative momentum. Yeah? this is the idea. Yeah, we take a pendulum, and then we put it on Earth, and because the Earth is moving inside of neutrino bars, it rotates around the sun. You should be able to see some daily or annual modulation in principle. Yeah, this is what we want to test. And if you measure this position of the pendulum mass with LIGO thermometers, for instance, yeah, which is the best instruments we have nowadays, in principle we might be able to test accelerations down to 10 to the minus 16 centimeters per second squared. Yeah, this is a number we came up, so it's like people would probably say we're stupid, but this is a number we estimated, yeah, based on their statement. In future, this might improve by a factor of 30 with Einstein telescope, yeah, but this is the future. It's like a 20, 30 years from now. So what about predictions? This is the crux, yeah. This is the problem. The prediction says in the most optimistic scenario, you can expect accelerations of the order of 10 to minus 27 centimeters per second squared, which is only slightly smaller than you can see in the experiment. So this is not really working so well. Yeah? But I don't have time to discuss this, but you could also in principle try to do this to look for that matter. But that matter we don't know how big the cross section is, we don't know the momentum, we don't know the mass. So there a lot of things are possible. Yeah? But the vanilla WIMP doesn't work as well. So when we're doing this, we're thinking about alternatives. Keep in mind, yeah, if I go back here, you see that the sensitivity is proportional to the G factor. So what can we do? Yeah, basically we say we just put it to space because they're very small G factors. But then since we're already in space and have so small G factors, let's say we just forget about the pendulum and just take free falling masses. And we take two free falling masses, the same mass, but they have different neutrino cross sections. And then they will drift apart, yeah, after time, because one will fit on neutrino wing and the other one will not. Yeah? But again, you would need something like 3 months of continuous exposure, and then they drift away a distance which you could see with LIGO, yeah? Which is of course probably not working because you cannot put LIGO to space and make it run over 3 months. And then there are alternatives to mechanical forces. The one I already mentioned is prisoner absorption, and let's move on to reverse beta decay, which is probably at this point the most promising proposal. Yeah, reverse beta decay processes. This goes back to Weinberg in '62. Yeah, this is old physics. This is really old physics. Yeah, this is older than physics. The idea is simple. There are lots of neutrinos around, and we know from beta decay, let's say for the tritium beta decay, you would admit, so you would get this tritium would decay into helium, and you would emit an electron and another neutrino. But you can also flip the sign around, this line around to the other side, and then you can do neutrino capture. You take a tritium, you capture a neutrino, and then you emit an electron and 3 helium. Yeah? So basically just flip it around. And then you hope, because there are many neutrinos around, that you can do this trick because, yeah, at some point you should get some effect. Yeah? The signal would look like this. You should measure the electron spectrum and the spectrum. You should measure the energy of the electrons coming out. And the electrons coming from the capture, they will have slightly more energy than the ordinary endpoint from the beta decays. Yeah? This is what you should see. You should see like some bump above the endpoint. Yeah? And you see this is the challenge is here to resolve the bump, because the difference between the bump and the endpoint is of the order of neutrino masses, yeah? Which at this point we cannot resolve yet. Yeah? Maybe in the future we can. So let me give you some numbers. This is based on this paper more or less. This Ptolemy collaboration, they want to use 100 grams of tritium, which is a lot of tritium, and that means they have a number of target nuclei of the order of 10 to 25, yeah? Which is a lot. And if you have this amount of tritium, you will expect, using standard cosmology, something like 4 to 8 events per year for neutrino capture. Yeah? You will expect 4 to 8 events per year. Yeah? Order 10. The background rate on beta decays within 0.1 volt of the endpoint is 2 Hz. Yeah? So this is still a major challenge. So the question is, how can you resolve the endpoint? And of course, if you have like a very good energy resolution, you could still say this 2 events, this few events per year. They are definitely higher than the endpoint, so you don't care. Yeah? But I'm not an experimentalist, so I just say this like very easy peasy. Yeah? Let's hope for the best. Yeah? Okay. Yeah. So, sorry, this is very sensitive. The current status of this experiment, let me just say this. So in March, this collaboration, they submitted a proposal to the Canzasto laboratory in Italy, and they proposed to achieve the proof of principle of the Ptolemy project. Yeah? So they want to ship the demonstrator, which is right now in Princeton. They want to ship it to Italy, and then they want to test all the components and basically demonstrate that they could build this experiment. Yeah? But what I was told is that it's not going to happen in Kansasu, because at Kansasu there will not be tritium. Yeah? So if you have some underground lab and you want to host an experiment, I think he would be very welcome, yeah, for them. Yeah, I would be very happy about this. Also, I'm not involved in Taiwan. I have no time, and this paper is not published, so this is why it's like all blurred. Let's move on. Summary conclusions. How can this be? Summary conclusions. I was too fast. Anyway, the CMB is one of the earliest creatures of the universe. Yeah, this is important. The CMB was produced 1 second after the Big Bang, while the CMB was produced 380,000 years after the Big Bang. So there's a huge gap in terms of time and energy. Yeah, so if we could see this, it would be very interesting because we could test a lot of properties of standard model of particle physics and also of cosmology. Yeah, and see if it's consistent with each other. There's overwhelming indirect evidence. This is good because if you look for it, you know that you have a high chance to find it. This is different compared to supersymmetry or compositics or whatever you're working on. I did this myself, so no worries. I know what I'm talking about. But there's no direct observation so far. Yeah, that must be said here. Yeah, nobody has seen this directly in experiment, which is and I guess you understand now why, because the numbers are all very, very difficult. From my point of view, and I think from everybody's point of view, the most promising example proposal so far is the Ptolemaic proposal. If you believe it's going to happen or not, I leave it up to you. But this is the only proposal which I'm aware of which gives reasonable numbers. Yeah? They say a few events per year, which is not impossible, a few events per year. Yeah? What I didn't have time to talk about, or maybe I had, if I would known before, the CMB searches can be dark matter searches as well. Because if you go back in history, yeah, how did people start to think about WIMPs? They were thinking about neutrinos. Basically, neutrinos are WIMPs, yeah? Just very light WIMPs. So when you do experiments, in most cases, you are sensitive to certain kinds of dark matter. Yeah? So even if you say there's a huge gap to fill to go for the cosmology background, you can fill this gap just looking for dark matter. And if you find dark matter on the way, I would say this is not a bad deal. Yeah? This would be not so disappointing. So you saw the numbers. You might say these numbers are depressing. Why I'm doing this? I did this because it was fun to work on this. Yeah, it's crazy ideas, and I learned a lot about physics doing this. So that's why I like doing this. And I think actually, I mean, all during the conference, many people said, we didn't find supersymmetry, we didn't find dark matter, we didn't find the compositics, we didn't find extra dimensions. So we have to think about new ideas. I think this is some kind of new ideas, and new ideas have the problem often that they don't work so well. Yeah? So we should keep on thinking. Yeah. So I think it's a good time to think about crazy ideas and then be very open-minded about the results and not get depressed if numbers are not so promising. Yeah. So I think now I'm good. Thank you. Yeah.
Thanks, Martin, for staying well within the time frame. And then any question for him?
So you are actually trying to detect the momentum of the collision of the.
Kind of, yeah.
So in fact, I think things may be better than what you said, because the thermal temperature is 1.9 K. That's from the Big Bang, but the neutrinos during the structure formation get peculiar velocity. So those peculiar velocities are about a few hundred kilometers per second, which is comparable with the dark matter. I mean the velocity in the Milky Way. So
yeah, actually you're right. Actually, that's the point. I didn't discuss this here, but it has different kinematics. So if they are like kind of heavy enough, they will cluster in the galaxy, and then they will get the variable velocity of the galaxy. So then they will get slightly more momentum. This is why I find 10 to minus 27. This is, of course, you can try to cook up some other scenarios, and there might other scenarios where they might get slightly more. But all the scenarios I know of, you might get like a factor of an order 1 factor, maybe an order 10 factor, but order of 10 to 10. If you have some idea.
So what is the velocity you assumed?
Here we assume 10 to minus 3.
So this velocity of light. Okay.
Yeah.
Okay.
10 to minus 3 times speed of light.
Yeah, that's probably right. Yeah.
And of course, they will go a bit higher if you want. This is why you have to scale.
Yeah, they're probably not any more higher than that.
Yeah, I can get a factor of 10 to 3, not more. Yeah, that stops for sure.
Okay, more question?
Okay. Yeah, it's usually on the big bang with this kind of topic, but can I is any progress on the idea that require the accelerating of a target? Since it is so slow, so one idea is accelerating a particle to keep this guy, right?
Yeah, I can show you the slide.
Yeah.
It's this slide.
Oh, excellent.
You have to wait.
Yeah.
You have to wait. Okay. But you can discuss afterwards. But I can also tell you it's not working.
Okay, so
it's not
I can discuss with you overnight, and happy to know it doesn't work.
It's not this. I mean, I can show you. Just tell you what. So we're thinking about muon beams, which can be and then we have high luminosity muon beams, and we found event rates of 10 to minus 20 per year.
Well,
almost there. Yeah.
We just need a super duper whatever collider to wait for 30 years.
So yeah, muon colliders they might have more luminosity by a factor of 10 to 6, 10 to 8.
Yeah.
But this is just 10 to 6 to 10 to 8. Yeah, and this is just the signal event rate. We don't even discuss about background and background discrimination. Yeah. So, but the signal is only like 0. Yeah.
Yeah, but it would be nice to discuss with your time. Yeah.
Okay, one last question.
There you go. Yeah, I have 2 questions. The first one is, because from a CMB measurements, we know they are layered. Is
Yeah.
it nice that proof already? And the second question is, regarding the pendulum, can you do that one for the solar, basically we know they are layered. Can you do that?
So let me answer the second question first. Solar neutrinos have 10 to minus, I think they have 10 to minus 26 centimeters per second squared. So they're like a factor of 10 better than the CMB neutrinos. And this is because the cross section is much larger and the momentum is much larger, but the CMB neutrinos get a coherence factor, which they don't get. So because they have very long wavelengths, so they scatter of multiple nuclei. That's why the CMB neutrinos are much better off than you would naively expect. I can explain more detail later. Yeah, this is just a short answer. Solar neutrinos are slightly better. The first question is, if it's enough, I would say that we already discovered the Higgs like 20 years ago. So what's the point, yeah? Looking for the Higgs. I mean, in the end, the point is, the question is the CMB background as we expect? This would be a way actually also to tell you if there are Majorana particles or not. This is the only source of non-relativistic neutrinos which we know of. Yeah? And if you have non-relativistic neutrinos, you can test Majorana nature by looking at the scattering cross-section. And you can look if neutrinos decay, for instance. This is
in this case, I would say majority stuff of the beta decay is more promising.
yeah, but you have the dip, and if you're on the dip, you are lost.
You always make it away from the dip.
In principle, yes, it's a principle thing, yeah. And then, yeah, you can test all kinds of properties. You can test if neutrinos decay with cosmological lifetimes, yeah. You can look how dark matter looked at this point more precisely, because in cosmology everything is washed out. You can always play around with parameters and say, okay, yeah, and then you have more neutrinos, and then this modifies, and then this would be like another independent test, and you can use it to better constrain cosmology actually, yeah, to make it more easy. I think in the lab everything's better. You can also ask, why is scattering running? Why don't they switch it off? Because they cannot find it, because cosmology said they cannot find it. Yeah? The same argument. The lab is better, always. The lab is better. That's the argument. Cosmology is complicated.
Okay, good. I think we have to move on to the next topic and then thank Martin again.